Hello, dear student. Today we will discuss about mobility within the same subnet. And as you can see here in this diagram, that we have a host H1 that is moving from BBS1 to BBS2. So this node host 1 is moving from S1 to S2, and definitely the connectivity of this node will be established with access point number 2. While here in the background, if you can see, the hub or the switch as well as the router remain the same for both access point. So the underlying network here remain the same, while other credential that include the access point is changing from access point 1 to access point 2. So let's start with this slide. You can see that the host 1 will remain in the same IP subnet, and the IP address of the host can remain the same, though he is moving from one access point to another access point. So in this regard, the communication that is going on in that subnet will remain uninterrupted as the switch is same. Similarly, host 1 recognize the need for change of a connectivity point. In this case, as host 1 is moving from access point 1 to access point 2, so gradually the signal strength of access point 1 will decrease and the signal strength of access point 2 will increase as the distance of host 1 will be minimizing with this movement. So host 1 detect this weakening of a signal, and that's why he actually starting the scanning of environment and looking for a new access point. So meanwhile, this is called the overlapping region in which access point 2 and access point 1, both signal will be detected by host 1. So after moving in that direction, access point 2 will actually share his credential, and the host 1 will also send the association request toward that access point 2. So onward, the access point 2 will provide connectivity to host 1. And as you know that the underlying network, or you can say the backbone network for this architecture is remain the same. So there is no need to actually change the IP address or other credentials. So this switch learn that here is the new location of this host 1, that now he is receiving the data or signal or information of host 1 from access point 2 instead of access point 1. So here is a self-learning mechanism that is adopted by the switch, that now he is receiving information or data from another access point. Now moving toward another topic, that is the carrier sense multiple access, in which important thing is that multiple station wants to transfer data at the same time. So sometime there is a possibility that both nodes start transmission of data at the same point, and the data they are sharing with one another collide on the link, and this collision actually destroy the data or corrupt data. For example, if we have these two computer nodes, and here is the communication link, and both of them want to transfer data to node number 3. This is node 3 and this is node 1 and 2. So at the same time, node 1 and node 2 both sense the media, and then they find that the media is free. So if the media is free, then they start transmission of data on the media. And meanwhile, when both nodes start transmission at the same time, then their data collide. Start transmission. At the same time, their data collide with one another. And this collision sometimes destroy the data as well as corrupt this data. So the receiver will receive data with some errors. So the data received at the destination node will be received with some error. So therefore, we actually use the carrier sense multiple access mechanism in which the channel is shared. Every host that want to transfer information to any other node will first check the media and then also inform its neighborhood nodes about his transmission to the destination node. So multiple nodes want to do transmission of data to the destination node. So the first responsibility of these nodes is that they should sense the media, sense the carrier, and then onward, if anyone is not sending data to any other node, that means that the channel is available. But for example, if someone want to or is going to send data to any other node, then the channel will look busy. So to stop or to avoid any collision on this ongoing transfer, we will use the detecting ongoing transfer, and once it is available, then we will stop transmission. And for example, if no one is transferring data to any other node, then we will attempt to transfer our data to the destination node. Here you can see we have node A, B, and C, and there is possibility that A and B are communicating with one another. Similarly, C send a request to B for communication. So if A and C both transmit packet at the same time, and the packet transmitted by C and A is received at the receiver antenna of node B, then there is possibility of a collision. And you can see here in this diagram, at this space, the signals are colliding with one another. The A signal is red and the C signal is blue. And over here, they are colliding with one another. So if they are transmitting data at the same time, then there is possibility of a collision, which may result in the destruction of packets or data, or which may result into the erroneous data generation. The collision detection in Ethernet or wired network is also in the same pattern, where station listen while they're transmitting to any other node, and whenever there is detection of collision, then they actually stop the transmission. So the transmission abort, and they will try again once they detect or they sense that the media is available. So here is a problem, that problem is called hidden terminal problem, where we cannot detect all the collision at the same time. Another problem over here is that the strength of received signal is much smaller or higher sometime that you are exposed to those signals That's why you couldn't transfer your data. If you are exposed to those signals, then there is again a possibility of a collision. So that is the problem of exposed terminal problem, in which you are exposed to the signal of other nodes that are already involved in a communication process with any other node. So actually, to address this problem, we have another protocol, that is MECA. The traditional protocol 802.11 doesn't do collision detection, and that's why we are moving to another important thing, that is MECA protocol. We will discuss it later. Now, moving toward the medium access control that is done in 802.11, where collision is avoided and not detected. Once a station starts transmission of data, then it needs more aggressive collision avoidance technique. For example, if you are waiting a little bit after sensing that the channel is idle, and there is possibility that someone may sense media and start transmission at the same time. Similarly, we can have another possibility of data link layer acknowledgement and retransmission, where CRC, that CRC stand for a cyclic redundancy check, that is used to detect the error, and the receiving station actually send acknowledgement to the sender if the data is received without error, our data is received properly in the form in which it was sent. Sending station retransmit if there is no acknowledgement, then there is a particular time out that is given, that once the time is out, then you should go for retransmission of that particular packet. And here is, sorry, here as we discussed about medium access control issues, so again, we will be discussing those specialized problem, that is the hidden terminal problem. There are many issues that need to be addressed in order to design an efficient MAC protocol, that is the medium access control protocol. And the first issue, as we discussed about the hidden terminal, and you can see in this diagram, we have three nodes, node A, node B, and C. So here, node A can hear B, but not C, as C doesn't come in the range of node A directly, but indirectly, it can access node C via node B. So just assume that A is sending some data to B. When C is ready to transmit, it doesn't detect carrier and thus commence transmission. As I told you that, for example, if A want to send to B and C also want to communicate with node B, then both A and C sense the media, so that they find that the media is free, and both transfer their data to node B. So there is possibility that they transfer data, and that packet collide at node B. So that is the problem of hidden terminal problem, that A and B can see each other, C and B can see each other, but A and C are unable to see each other, as they are not directly connected with one another. So therefore, it doesn't detect carrier and thus commence transmission, which result or produce a collision at node B. So node B may not receive any data, or node B may receive partially correct data with some error. So here you can see that node A is going to do the transmission. Their A send information to B, and it can't detect A's transmission. The C node can't detect the transmission of A. Meanwhile, when C want to transfer data to B, it sends the media, and look at this, the media around here is free. So when he send his information, then there is collision at node B. And in that sense, or in that case, the CS, that is the carrier sense mechanism, fails. There is collision at node B, and A can't detect this collision as a collision detection also fail in that case. And the main reason behind that is that A is hidden from C and C is hidden from B. Another important problem here is the exposed terminal problem. And here you can see the scenario is a bit different. We have added node D, and node B want to transfer data to node A. So, and C want to transfer data or want to communicate with node D. So B send to A, and C want to
overnight challenge in a trampoline park. So be sure to give this video a big thumbs up right now if you would join us in this challenge. And yeah.
New Excellence Ash Supreme. Fight brass week after week. New Excellence Ash Supreme by L'Oreal.
So here you can see that B sent to A while the C want to communicate with node D. There is no involvement of node C with node B. A and B are involved in communication with one another, and C and D want to communicate with node D. So C actually sends this carrier and find that the medium is free on other side while it's in use and it is exposed to node D. So therefore, C finds that the medium is in use by node B. Therefore, he go to a waiting state. But then if you have a look to the node positions, node A is outside of the range of node C. So the communication of node C will not affect the communication of node A. Therefore, wetting should not be necessary. But if you have a look that node C is exposed to node B, therefore node C stop its communication with node B. And that's the reason that node B can communicate with node A, but C can't communicate with node D. So to address this problem, actually we have we will discuss this multiple access with collision avoidance. That is the MECA protocol. So this MECA protocol actually use two types of signaling packet for collision avoidance. The first one is RTS, that is called request to send, and this request is sent by the sender node, and the main purpose of this request is to check the availability of the receiver, as well as inform other nodes in the neighborhood that he is going to start communication with this node. So sender requests the right to send from a receiver with a short RTS packet before it sends a data packet. Another packet is a CTS, that is clear to send. When receiver receive this RTS, it grants the right to send or to start the communication process to the sender as soon as possible, and therefore it informs the sender that the receiver is ready to receive his data. So this signaling packet actually contain the sender address, who will be the sender in this communication process, who will be the receiver, and then the duration of communication as well. So the duration of communication actually realize to the neighborhood nodes that they can communicate after this much time. For example, if the duration of communication is 5 minutes, then the neighborhood node who are waiting for communication with node B or node A, then they should sense the medium after 5 minutes because the medium will be available after the duration they have mentioned in this packet. So here is the solution provided by MECA protocol. MECA avoid the problem of a hidden terminal, and you can see here in this diagram where A and C want to send data to B. So first, the RTS request to send packet is generated by A and received by B. So this RTS is not received by C, as C is out of range of node A. So when A send RTS to B, request to send, then B in response send a CTS or broadcast a CTS, which is received by A and received by C node. So CTS received by C node have the information that sender is B, sender is A, receiver is B, and the duration of this communication is 5 minutes. So now the C will wait for 5 minutes, and after 5 minutes, when this communication ends, then the B will be available to communicate with node C. Here is another problem, that is the exposed terminal problem. And you can see that Mecca also avoid the problem of exposed terminal where node B wants to send data to A. And here you can see that RTS is generated by node B, and this RTS is received by node A and C both. This RTS has information, as we discussed earlier, that sender is B, receiver is A, and C only get the information that this communication between A and B will take 5 to 10 minutes. So it's the responsibility of node C that he should wait for next 5 minutes. Meanwhile, node A transfers the CTS clear to send to node B, and they start communication process. So AC is not a part of this communication, then he can start his communication with node D. So C node received the RTS, but no CTS. Now C doesn't have to wait, as it cannot receive the CTS from A, and therefore he is able to start the communication process with the node D. Now we will discuss about that why ad hoc network is more important or more acceptable in the community are the people who are working in this area. So the first important thing is that the implementation or the deployment cost, that we can say that setting up fixed access point and backbone infrastructure is not always viable. While on the other side, if you have a look to ad hoc network, there is no infrastructure cost. Infrastructure may not be present sometime in a disaster area. For example, there is a war zone, there is flood, there is earthquake, there is any natural disaster in that particular area where no infrastructure is there, or sometimes the existing infrastructure may be destroyed. Sometime if you are going for a short period, then infrastructure may not be practical for short range radio or for some time. Sometime you know about these military exercise where they go for exercise in deserts, in oceans, or in mountainous area just for a month or two. So then the infrastructure deployment may be very costly. Therefore, they encourage to use the ad hoc network for communication. Therefore, ad hoc network provide all the necessary backbone facilities and all the necessary infrastructure facilities. As the ad hoc network don't need the infrastructure support, therefore they are very easy to deploy, and they are very useful and easily manageable where the infrastructure is absent, destroy, or impractical. Here we can see a comparison between the cellular network and ad hoc wireless network, and you can see that in cellular network is very expensive as compared to ad hoc wireless network. We have fixed infrastructure in cellular network, while ad hoc is infrastructureless and you can easily deploy them. There is guaranteed bandwidth in a cellular network, while ad hoc network works on a shared radio channel, or you can say on the best effort delivery. The cellular network is more centralized, more controlled by the servers, while in ad hoc network we have distributed routing, and the network by itself tries its best to deliver data through a shortest path. Now, here is circuit switching, where a connection is established before communication, while in ad hoc network we have packet switching. Similarly, in cellular network there is seamless connectivity where low call drop and specifically handoff procedure is a bit more efficient and more reliable. In ad hoc network, there is frequent breaks, and the main reason behind that is that you have different neighborhood or neighbors in your surrounding. When you move from one point to another point, therefore, first you have to discover those neighbors and then onward to establish a connection with them. In cellular network, we have very high cost and a very time-consuming job when we deploy these networks. While ad hoc wireless networks are more quick and cost-effective as compared to the cellular network. Similarly, application domains include mainly civilian and commercial, while ad hoc network application include battlefield, emergency, search and rescue operation, and collaborative computing. Similarly, we consume much more money on the maintenance of cellular network, while ad hoc network is self-organized and we don't spend too much on its maintenance. Mobile hosts are of relatively low complexity, as most of the work is done by the backbone and centralized devices and servers, while in ad hoc network, a node by itself is a sender, it's a receiver, it's a switch, it's a server, it's a router, it's a gateway. So therefore, these nodes have more responsibility, and we need more intelligence devices in ad hoc network, that they can decide by themselves that what decision should be taken in a particular scenario, as they don't have any support from the infrastructure. Another important thing about cellular network is that major goals of routing and call admission are to maximize the acceptance ratio and minimize the call drop ratio. While in ad hoc network, the main focus is on routing to find path with minimum overhead and also quick configuration of broken paths. Cellular networks are widely deployed and now moving toward its fifth generation. While in ad hoc network, there are still several issues that need to be addressed in the research, and that's why it's nowadays a hot area in the research. And specifically, about the IoTs and its deployment in smart home, in smart cities, in smart vehicle, and in smart environment or smart industry, that is called industrial IoT. The deployment of these networks is still under research and need more and more improvement. Now, moving toward the next slide, that is the ISM band. ISM stands for instrumentation, scientific, and medical. That is an unlicensed band which is used for experimental purposes. If you have a look to the frequency ranges, we have a small band over here that is 26 megahertz. And this band is 902 megahertz to 928 megahertz. Another band in a bit higher frequencies, that is in gigahertz, 2.4 gigahertz to 2.48, that is almost 83.5 megahertz band. Another important thing is a 125 megahertz band, that is more higher frequency, that is 5.7 to 5.8 gigahertz. If you have a look to these three bands, then they are particularly used for scientific purpose. And if you want to do experiment of any device, then you can use and do the necessary experiment in this area. And this band is actually reserved for that particular purpose. Here you can see in this diagram the evolution of wireless communication. It was started on x-axis. If we can have a look, we have years, and on y-axis we have the wireless capacity and the throughput of these networks. So it started back in 1970s. Then we moved to analog communication. then 2G with the CDMA and GSM technology, and then the 3G with WOCDMA and GPRS, and in next that is 3.5G and 4G with the LTE technology, and then onward 5G. That now Wi-Fi 6 is actually part of this communication process. And if we have a look to the trend, then continuously the throughput is increasing, as well as the capacity and the speed of this communication model. So this is very important to know about this history, that how the communication, our mobile communication started, and where it stand for. Here you can see that today's Wi-Fi and 802.11 AC, which makes the beam forming rather than throughout wireless signal equally in all direction. So this beam forming is a very important technique to save the energy of nodes and don't disturb the neighborhood nodes who are not involved in this communication process. Wi-Fi with beamforming detects where devices are and intensify the signal in their direction. So that is very important to save energy as well as resources of other devices in our neighborhood. And we should only engage those devices which are part of this communication process. Now moving toward the power management capabilities of these wireless nodes, a wireless radio can perform one of the 5 activities. And look at this, that the power consumed by these activity increases in a given order. And for example, you can see a sleep mode of a node. The second one is either it's idle and awake, but it's not part of the communication process. Neither the node is sending, neither it's receiving, nor it's moving, mobile, or even you can also add the forwarding mechanism over here as well. Another important thing is receiving, the transmitting, and the mobility of these nodes. Let me share it a bit with the whiteboard. And here we have different types of nodes in this communication process. That's why, for example, if we have a network over here, the modes of these nodes, they can be active, they can be passive, they can be in sleep mode, and they can be dead. So look at this. If, for example, the lifetime of every node is 1 hour, if it continues to move. So for example, if all these nodes are in active mode, then the total network life will be 1 hour. But now if we manage that one device will be active here, for example, in first phase, that is the scheduling mechanism. That we schedule this node that in first phase 1, 3 nodes will be active. In phase 2, the next 3 nodes will be active. And then phase 3, the next 3 nodes will be active. So for example, if these nodes are active in phase 1, let me write 1, 1, and 1. And these nodes are active in phase 2, phase 2, phase 2. Then these nodes are active to report about any event in phase 3. So look at this, we have increased life of network from 1 hour to 3 hours. So we increase the life by 2 hours only do this scheduling mechanism. We have done nothing. We just schedule the modes of operation of these nodes, in which active state for the node is involved, where active means that node is involved in transmission, reception, or you can say as a forwarding node or as a router node. In passive mode, the node is not transmitting, not receiving anything, but it is actually on. It is not the part of not part of communication process, not part of communication process. Similarly, if we have a look to a sleep mode, then this is the low power mode, that node is neither active nor passive. And similarly, dead node means that the node is dead, which means that is energy is fully exhausted, and he has no more power to be part, no more power to be part of the communication process. So these are the few important categories that you should know about. And look at this, that asleep, idle, wake, receiving are the transmitting and mobility. So now moving to the next one, if you have a look, that allow idle station to go to sleep mode, and that is the scheduling mechanism that you save the power of these nodes and extend the network life. Similarly, access APs, buffer packers for sleeping station. So the access points which are alive, they can store the messages received for those nodes who are in sleeping mode. Access point announces which station have frames buffered, and then onward, the traffic indication map is an information element shared with all nodes. So this traffic indication map actually provide information about these access points, that which node have data with that access point. And then onward access point is responsible to deliver that data to the particular node. So that is very important, that power saving station should wake up periodically after some time, as we have discussed in our last example, that there is 1 hour gap between these power saving states, that they should change their state from active to sleep or sleep to active, and they should participate if they are part of the communication process. But if they are not part of the communication process, then they should go in sleep mode to save their energy. Here you can see the detail of traffic indication map, and the format of this traffic indication map is given over here, where we have element ID, length, DTIM count, DTM period, bitmap control, and partial virtual map. And you can see the detail of every element here, that the ID is the value 5 indicate in the TEM that definitely show the particulars of that node. Then onward the length, which length of the other information carrying field and the traffic indication map. And then the incremental beacon frames for next delivery, then the number of beacon frames between that DTIM, and then the bitmap control, which is used to indicate the multicast or broadcast information that are buffered with the access point. Similarly, the next partial virtual bitmap series that is used for flag indicating whether each associated state has unicast frame buffered at the access point. So the first bitmap give us information about the broadcast and multicast, and the next one give us information about the unicast information. So here in this diagram, you can see that the station received data and that is buffered on this access point. And it was initially in the sleep mode, and once it become an active node of this network, then all the buffered frames will be transferred to the node automatically. Here, the station in next diagram 8.10, you can see that station returns to the doze state where node is again going toward a power saving mode, you can say. And that's why he's also communicating to the access point that I am going back into the power saving mode. Therefore, if you receive any data for me, then save it with yourself. So next one is the host mobility. I think it is enough for today's lecture. And then next we will start about the host mobility. So thank you so much. If you have any question, you can share through email and I will reply you back. So thank you so much.